All right, Chapter 9 homework. Chapter 9 has a pretty wide variety of topics in it, so let's get started. Chapter 9 homework starts with the question section and question number 3, which says the same force is applied to two cylinders that contain air. One has a piston with a large area, the other has a piston with a small area. So we have our large area piston and our small area piston. In which cylinder will the pressure be the greatest? And we have to explain why. Well, we know pressure equals force divided by the surface area. And we have the same amount of force acting on both. So if the force stays the same, but this one here has a small area, and this one here has a big area, the one that's got the smaller area has a smaller number on the bottom of the fraction, which means the pressure will be greatest in this one. So pressure is greatest, right, in that one, with the one with the smaller area. All right, next, question 5. Why are bicycle tires often inflated to a higher pressure than automobile tires, even though the automobile tires must support a much larger weight? Well, I've drawn here a bicycle tire on the left and a car tire on the right. And notice that the surface area that's in contact with the road is much smaller for the bicycle than it is for the car tire. And not only that, there's only 2 tires on the bike, so that's reducing the surface area even more since there's 4 tires in a car. So the area in contact is much smaller, so the area is much smaller for the bicycle, and since pressure equals force divided by area, even though the force on the bicycle, the weight that it has to hold up, so the force that it needs to provide is smaller, the area is much smaller, so it requires more pressure to support that amount of force. And question 11. Which animal would you expect to have a higher blood pressure, a dog or a giraffe, and explain? Well, a dog is a much smaller animal, so the heart would have to pump the blood, doesn't have to pump the blood as far or as high. And we know in order to do that, for the giraffe to pump the blood up higher and farther distances, it's going to take more pressure to do that. So we would expect the giraffe to have a higher blood pressure. And question 20. A block of wood is floating in a pool of water. Here we have our block of wood and our pool of water down here. Question A asks, is the buoyant force acting on the block greater than, less than, or equal to the weight of the block? Well, we know that the acceleration equals 0. It's just floating there, 0 meters per second squared. And if F net equals m times a, and a is 0, m times a is 0, which means the net force is 0. And if the net force is 0, that means that any forces that are going up must equal all the forces that are going down. The force going down is the force of gravity, or the weight of the object. And the force up is the buoyant force, which you read about and we covered in class, buoyant force from Archimedes' principle. So since the net force is 0, the force down has to equal the force up. Therefore, the buoyant force is going to equal the force of gravity. It's going to be equal to the weight of the block. So for part A, buoyant force is equal to the weight of the block. Part B asks, is the volume of fluid displaced by the block greater than, less than, or equal to the volume of the block? Well, notice that the block is not entirely submerged. Only this part of the block is under the water. So only that part of the block has moved water out of the way. So the volume of the water displaced is going to equal the volume of the block that's underwater. But the block as a whole has more volume. So volume of the block is greater than volume of the water that it displaces, the water that it moves out of its way. All right, question number 26 has to do with Bernoulli's principle. Question 26 says, why does a stream of water flowing from the faucet often get more narrow as the water falls? Well, Bernoulli's principle says that as a fluid is moving faster, it feels less pressure. It's one of the reasons why airplane wings work, and something we talked about when we had our disc golf lesson. So, as the water is falling, it's accelerating downward as it's getting closer to the bottom here. It's going faster and faster, and therefore pressure at the top is going to be greater than the pressure at the bottom. Pressure down here is reduced. And when the pressure goes down, the atmosphere, which is pushing on all directions on this water, is going to constrict it more because it's feeling less pressure. All right, on to the exercises. Exercise 1, we have a 40 Newton force pushing down on a piston that has a surface area of 0.5 square meters. And we're asked what the pressure is, or what pressure does this produce inside of the piston. The equation for pressure is force divided by surface area, and we have both of those quantities. We have a 40 Newton force and a 0.5 square meter area. 40 divided by 0.5 is going to give us an 80 Pascal pressure. Pressure equals 80 pascals. Exercise 10. A 0.47 kilogram block of wood is floating in water. What is the magnitude of the buoyant force acting on the block? So we have water, we have block. So we have the weight, the mass of the block. Mass equals 0.47 kilograms. And we know it's floating. It's not accelerating, so we have the downward force of gravity. And we have an upward buoyant force. And since it's not sinking and it's not actively accelerating upward, it's at equilibrium, we know that the buoyant force is going to equal the force of gravity, which equals m times g. So I take my 0.47 kilograms multiplied by 9.8 meters per second squared, the acceleration due to gravity, and I get 4.61 newtons. Exercise 12. Exercise 12 says a certain boat displaces a volume of water equal to 6.7 cubic meters. The density of water is 1,000. So density of water is 1,000 kilograms per cubic meter. Part A asks, what is the mass of water displaced? So density equals mass divided by volume. So the mass is going to equal the density times the volume. So we end up with 6.7 times 1,000, and we end up with 6,700 kilograms of water. Part B asks, what is the buoyant force acting on the boat? Well, the buoyant force equals the weight of the fluid displaced. So weight is equal to m times g. The mass of the fluid displaced is 6,700. G is the acceleration due to gravity, which is 9.8. So we get 6,700 kilograms multiplied by 9.8 meters per second squared, and we get 6,500 newtons, 65,600 newtons of buoyant force. E14. Exercise 14 says a stream moving with a speed of 1.2 meters per second reaches a point where the cross-sectional area of the stream decreases. So if I'm looking at it from above, the stream narrows. So we start with an initial velocity equals 1.2 meters per second. And the area narrows to 1/3. So if it was initially area of A, it ends with an area of 1/3 A. What is the speed of the water in the narrowed portion? So I'm going to change to red. What is the speed here? So V2 is a question mark. So we know that the fluid flow, AV, is conserved. So A1 V1 equals A2 V2. The area times the velocity equals the area times the velocity. So if you take area times velocity, you end up getting the volume per unit time, which is the fluid flow. But we're trying to find V2. So we're going to take V2 equals A1 V1 divided by A2. So what do we have for numbers? A1 is just the area. We don't know what it is, but we know it's just A. V1 is 1.2 meters per second. Area 2 is 1/3 A. So now we have an A on top, A on the bottom. They cancel each other out. And we end up with 1.2 meters per second divided by 1/3. Dividing by 1/3 is the same as multiplying by 3, and we end up with V2 equals 3.6 meters per second. All right, finally, synthesis problem number 1. Synthesis problem 1 says we have an input piston on a hydraulic jack with a diameter of 2 centimeters. And it's a little hard to read, but this says 2 centimeters. And we have a load piston on the other side with a diameter of 25 centimeters. The jack is being used to lift a car, and the car has a mass of 1,400 kilograms. And we have 4 parts, A, B, C, and D. Part A says, what are the areas of the input and load pistons in square centimeters? So we know area equals pi times r squared. That's given in the problem. But we don't have the radius. We have the diameter. Remember from your math classes and throughout your schooling that diameter equals 2 times the radius. The radius is just half of the diameter. So for the first one, this 2 centimeter diameter has a 1 centimeter radius, and the 25 centimeter diameter has a 12.5 centimeter radius. So for the piston on the left, the area equals pi times 1 centimeter squared, and 1 squared is just 1, so the area is pi, or about 3.14 square centimeters. And the one on the right, we have area equals pi times 12.5 centimeters squared, which is about 491 square centimeters. All right, part B asks for the ratio of area of the load piston to the input piston. So a ratio is like a fraction, so ratio is going to equal the area of the load piston, which is 491 centimeters squared, and divide that by the area of the input piston, which is 3.14 centimeters squared. All right, and that gives us a ratio of about 156 1/4. And the units cancel out, so it's just 156 1/4, 156.25. There's my answers. All right, part C says, what is the weight of the car in newtons? All right, we know that weight is the force of gravity acting on something, which is mass times the acceleration due to gravity. We know the mass is 1,400 kilograms, and the acceleration due to gravity is 9.8 meters per second squared. Multiply those two things together, and we get a weight of 13,720 newtons. All right. And lastly, part D. What force must be applied to the input piston to support the car? Recall earlier in this chapter we talked about how the pressure in the inside of this fluid is the same throughout. So the pressure that's being applied on this side is going to equal the output pressure on that side. So the pressure from the left-hand piston is going to equal the pressure out on the right-hand piston. And pressure is force divided by area. So force on 1 divided by area 1 is going to equal force 2 over area 2. So the pressure at point 1 is going to equal the pressure at point 2. We know the force on the right piston is going to be the weight. So force 2 is going to equal 13,720. And we know the area of both of them because we calculated that. So we can solve this for force number 1. That's what we need to get to. So force 1 is going to equal force 2 times the area 1 divided by area 2, which is going to equal 13,720 newtons times area number 1, which is 3.14 centimeters squared, divided by area number 2, which is 491 centimeters squared, which gives us an input force of 87.8 newtons. And that's all. If you have any questions, send me an email. Don't hesitate to ask.